All right, so let's process some data from this part one of the Enthalpy Lab. So I cheated a little bit. I copied the data table off of the graphical analysis software and I put it in Google Sheets, which if you're doing this for an IB recommends that you do that anyways because it's easier to see the data and it's considered data processing. So what I went ahead and did is I cut and pasted this data in here. I titled each of my columns. The first column was time with an uncertainty of plus or minus 0.1. And the second column was temperature with an uncertainty of plus or minus 0.01. So this is a great review on how to graph. The reason why I'm going to graph for this lab is because even though I can see the initial temperature at time 0, and I can scroll all the way down and find the maximum temperature way at the bottom, we have to assume that this reaction happens instantaneously. So that's not captured when you're collecting data on a vernier because over time that temperature changes. We want to pretend that the temperature change happens instantaneously, so it goes from a minimum temperature to a maximum temperature all in almost the exact same time period. And I'm going to show you how we can use a graph to figure out what a true change in temperature would be and not a change in temperature over time. So here we go graphing. I'm going to highlight these two columns. I'm going to insert my graph. And you'll notice here that it is set up as a line chart. I really would rather a scatter plot, even though the graph will look the same. And that's because I can make it a little bit bigger and realize that each one of these dots is actually a moment in time. And remembering tails, title, axes, increment, labels, scales. My title is correct. I have my y-axis versus my x-axis. I labeled my axes. My increments are done for me on Google Sheets, as well as my scales. So this is a pretty good high quality IB graph here. The data is not great, however, but this is raw data. This is the data that I collected during the investigation. So this is what we're going to use, because this is what you would do if you were here as well, using data that you don't even like as well. So if I notice right here, right about this point, is time 0, even though it's not on the y-axis. And that's because that's the lowest minimum temperature right there. And see if I can get that data point highlighted. It's in there somewhere. And then I've got a maximum temperature. And the maximum temperature will be here like this. And I notice right after the maximum temperature, I'm starting to have a pretty steady decrease in temperature at the very end. And that's because due to time constraints and people calling me during Zoom, because I am multitasking, I took the lid off the calorimeter. So error. What we're going to do is we're going to figure out the true final temperature by using the maximum value here and the minimum value here. And I will show you how to do that in a moment. All right, so what you are seeing here is a graphic that shows you how to extrapolate backwards on a temperature time graph to find the true final instantaneous temperature of a reaction. This is called the two-tangent method. Here's tangent line number 1 that you draw right after you reach your maximum temperature and the temperature starts to drop. And here is tangent line number 2, which is tangent to your initial time 0. Where those two tangent lines meet, you will get your true final temperature. And that's the final temperature that you want to use in your CUMSAT equation. However, with the data that we collected, the two-tangent method is not going to work. And the reason why the two-tangent method is not going to work is because your illustrious teacher took the lid off too soon. And if you notice, if I draw here a tangent line, it's going to go way above where it should in terms of what the final temperature should be. It's going to go way off the chart. So far off the chart, it won't even draw for me. So the final temperature would be way up here, 50, 60 degrees Celsius. And I know for a fact it didn't get that high. And the other line that I would draw would be here like this, where the initial temperature would be. And that final temperature that would occur way up there, way off the chart, is completely erroneous. And once again, that is because I took the lid off of the calorimeter way too soon. So instead of using the two tangent method in order to find the final temperature, we're going to just do our typical read the graph scenario. So here's my graph again, and I'm going to find that point right there, which is going to be my minimum temperature of 18.23. Notice it's a little bit lower than the time zero here. That's my true initial temperature, is that 18.23. And then my final temperature, I'll just do right where I see the graph starting to drop. So my final temperature will be 26.60. So on the next slide here, what you're going to see is all of the data laid out for you and what your task is going to be after that. All right, so here's what you're going to do next for this lab. So remember, whenever we're doing a calorimetry lab, we've got a system and a surroundings. The particles here represent the system. The system in this case is the copper sulfate pentahydrate and the zinc. The surroundings is going to be the water, the calorimeter. I didn't find a picture of a calorimeter. Let's just pretend it's the beaker there. The temperature probe, the lid, the stir bar, all of that stuff is going to be the surroundings. So with that being said, we want to figure out how much heat is going to be transferred from the system being the reaction, to the surroundings. And if we know that amount of heat, we could figure out the molar enthalpy value using the data below. So the data that I'm providing you is this. And this will be spelled out for you in the lab I'm giving you. I'm giving you the volume of the solution of copper sulfate. It was 75 milliliters. I also should tell you here, that the quick little adjustment there, you'll see that the volume of the 0.25 copper sulfate solution is going to be 75 milliliters. You're going to see here that you've got a density of solution of 1.00 grams per cubic centimeter, basically the density that of water. So that means that we're going to use a specific heat value, that of water, of 4.18 joules per grams degree Celsius. My initial temperature was 18.23. My final erroneous temperature was 26.60, because remember that I lifted the lid off the calorimeter, and so that didn't allow us to extrapolate back to get the correct final temperature. This is the mass of the zinc plus the whey boat. This is the mass of just the whey boat. When I subtract those two masses, remember that I have to add absolute uncertainties. So now that I've got my raw data, let's see what we're going to do. So you'll see here, you're going to get a copy of this raw data on a Google Sheet, and you're going to create your own practice graph with my faulty data. That's just because I want you to practice graphing, because if you need to include a graph with your IA, it's a really good skill to have. You're also going to know that the heat gained by the surroundings, the water, is equal and opposite to the heat lost by the system. So then you're going to calculate the heat lost by the reaction using CubeSat. You're going to use this value in order to come up with the enthalpy of reaction for the reaction of copper sulfate plus zinc. This is going to be a limiting reactant type problem. So you have to figure out how many moles of both the copper sulfate you've got, how many moles of the zinc you have, and figure out which one limits the amount of copper you will make inside of that cup. Using that information, you're going to calculate the delta H value, the enthalpy of reaction, and then you're going to compare that against the lit value for this reaction, which is negative 217 kilojoules per mole. I'll give you a hint. I know that a few of you were frustrated last lab because you said, oh, Miss J, your data looks so great, it's almost perfect. It's not going to be that way this time. And so you will see that I make mistakes as well. And my percent error for this one is going to be really, really high. So you'll feel better that it's not always the case that the lab is done okay by your instructor as well. So this is all spelled out for you in your copy of the document. Enjoy.